Hey guys. See that Jake has already said something? Let's see. Let me fix my lighting. Still in my college dorm room, but I'm gonna wait for 9:05 Eastern time to officially start. Just like say something in the chat if you can hear me properly. Okay. Hey guys. Okay, Jake, you're in the right place because every Thursday is just problem night Thursday. So I'm just here to like solve all your problems. Well, not really solve all your problems, only your physics problems. But I'm here to solve your physics problems. Just anything you have, just throw it at me. I'm free to solve. But I'll start at 9:05 so everyone is here. So I'll be solving your question first. Let's see. There's a ask a question here. Oh, you can hear me? I actually don't quite understand like this question and answer thing on Crowdcast because I don't know. They explained it to me. I just don't like it. So if you could say everything in the chat. I don't know how to use this at all, so I'm gonna just leave it. How are you guys this week? You guys doing good? Any tests? Everything? You guys are all taking AP Phys. Oh yeah, tired, of course. Got a quest. That's a good way to say it. Who's asking more questions when I said to not ask? Yes, test tomorrow. Kaden, where are you writing? Right in the. There's a group chat on the side just for you. But yes, test tomorrow. It's okay. You can throw any concept at me you want. It's actually my. Dang, that's annoying. Test and quiz in between. That doesn't sound fun. You guys are all in high school, right? Yeah, I mean, AP Physics only exists in high school, so. Oh yeah, don't worry, man. This technology thing is like hard. Like 10th grade, they're already taking AP Physics. That's pretty good. Honestly, props to you, man. Uniform accelerated motion, please. Of course. That's actually the lesson topic this week. I think we're covering. Like, what was it? I forgot my company's name. Fiveable has like this curriculum set up, and that is currently this week's curriculum. So technically, if you guys don't have enough questions for me, I'm just gonna go off for an hour on velocity and acceleration. 12th grade, that's when I took AP Physics. Are you guys also taking AP Physics C, or is that like a two-year thing for you guys, or like a 1 year thing for you guys? AP Physics C right now. Were you guys here last week? Any of you guys here last week? Are who is new and who was here last week? I feel like everyone here is new. Yeah, it feels like a fresh batch. It looks like I've retained no one, but that is okay. Let's see if I can like get you guys to come back next Thursday. Cause like I'm just like out here giving you free tutor, but like I'm just at your service for 1 hour every single week. So I think we have a decent amount of people. Your AP Euro teacher showed me this site. Yeah, it's honestly really good, especially if you want to self-study things. Like I know there's like always those horror stories of like bad teachers, like they don't teach at all, and like oh I'm not prepared about the AP test. This is like kind of an alternative that gives a full course load. Oh yeah. Ooh, that's some tea, but yeah, it kind of it'd be like that sometimes. Yes. I mean, like, okay, currently dying. My philosophy on life is that dying is the process of living, and living is the process of dying. So, in fact, you are living. In fact, if you're dying very quickly and very aggressively, you are living very aggressively and very fast. Yeah. I never took Euro. You're scary. Because you guys are all new, let me pull up my intro slides. Just like brief intro stuff. Have you guys like used Fiveable before at all? Oh, 95 is good. No? No? Yes? Yeah. Okay. But regardless, I'm pulling up PowerPoint. I might as well start right now. I think there's a substantial enough amount of people. Okay, let's do some screen sharing. Ooh, I'll be honest with you, like, I'm just like a streamer, so I don't know anything about this like plus thing, but I guess you can like rewatch my videos and see like all of the mistakes I do. I haven't made a mistake yet. I've done 2 streams. I haven't made a mistake, I think, possibly, but yeah, you can see me in my, listen to my monotone voice again as many times as you want. Okay, you guys can see this isn't, you can tell that like I've been recycling this PowerPoint like multiple times. If you look at like the file name, it's 9-3 stream, and like it says practice night 9-5. Oh no, I'm not gonna pop up any questions for you, but I'm gonna just screen share this right now. And because I don't like the presentation mode, I might just keep it like this. So I'm gonna just like go ahead and start. Okay. So first off, I'm like told to say this. Follow Think Fiveable, but something that I'm not told to tell you. No one told me to say this, but the memes on the Instagram page are actually very good. Like legitimately, like as a teenager in meme culture, these are like new and fresh memes. Like I don't know who's making them. They're very good. I give you my word. So go follow them on social media, particularly their Instagram. Just a brief intro about myself. I am currently a sophomore in college. In fact, I used to be a high school student 2 years ago. I graduated in 2018, and I'm actually originally from Henderson, Nevada, or like you might know like Las Vegas better than Henderson, so maybe just like think of me as from Las Vegas. I'm currently a sophomore at Columbia University, so that's just like me like flexing at you guys. Yeah, I go to Columbia. I do go to Columbia University. I'm in my dorm room right now. It's Thursday night. I'm probably gonna study mechanical engineering. So technically, I'm taking mechanical engineering courses right now, which is basically like the AP Physics content, but on steroids and like a little bit terrifying. But what I'm trying to say right now is like I am completely up to date with like all the AP Physics stuff. Like it's not like I haven't done like acceleration and velocity in 2 years. Like I'm doing it right now, except on steroids and like with very advanced calculus. It's absolutely terrifying, but let me tell you, I think I can handle AP Physics content. My favorite subject in school is physics. That's why I'm a mechanical engineer. I think I might become electrical engineering, but we'll see what will happen. But a fun fact, I did take AP Physics 1 before. I took it my senior year, and luckily enough, I did get a 5. So yeah, I did take this test before. So I'm just another student, just like out here, just like helping you guys. Let's see. Yeah. I feel. Okay. So the way that I like to set up my stream, let me change screen. I'm gonna oh, I actually don't know how to use technology. Okay. I have like the exact same problem every single time I stream. Oh, wait. I'm having a slight issue. Let me close some tabs because I have like 500 tabs open. That's probably why it's not registering my MS Paint canvas. You know what? I trust you guys because like this streaming thing isn't showing up my MS Paint canvas. Let me close this. Let me try to share screen again. I'm trying to. Yeah, so I'm having like slight technical issues, but that only means I'm gonna share my entire screen. So you're gonna see everything I see, which means you're gonna see the chat that I'm seeing. So it's a little bit informal, but this is because like Crowdcast is being stupid. But yeah, okay. You see what I see? Yeah, so you're seeing the screen that I'm streaming along with your chat. So I'm gonna open up this guy right here. So these are practice problems I have set. Oh, gosh, Crowdcast was working last week. They pulled up everything correctly, but this time not quite. So let me just open up a new canvas. Oh, gosh, I don't know how to use technology. Hold on. MS Paint is my favorite like image editor, whatever. It's just so powerful and easy. Okay, let's see. Jake F, you asked a question a little bit earlier. I know it's weird to ask right now, but I got a question on a worksheet that gave an initial velocity of 8 meters per second, and it hit a 5.3 meter wide spot of friction. Then the velocity was 6. It asked for acceleration. Okay. I'm a little bit confused with this one. So you got a ball, right? 8 meters per second. It hit 5.3. Did it hit like a wall? Like, and then it bounced back? Like what's happening here? Yeah. Please do. So is it like rolling and there's like friction, and then it became 6 meters per second. Like it was 8 meters per second, and it was rolling and it became 6 meters per second. Is that what happened? Yeah. Also, like, I'm assuming that Jake F is like typing these out right now. But if you guys have like a test or like a homework problem you're stuck on, like feel free to ask me within the next hour. Yeah, no problem. But yeah, just feel free to ask me. I'm just out here to like help you guys out. Like I have like no obligation to like, and just like feel free to ask me anything about physics, even like just general physics questions. I most likely will know. But yeah, do the rest of you guys have like any like problems or questions to ask me yourself? Like you can tell me a concept you're going to test on, and I can tell you some tricks. Like I went over like this really nice trick I always use for kinematics problems: tangent lines on velocity graphs. Okay, that's just like the derivative of velocity, right? I mean, okay, you guys took calculus before, right? A tangent line. Oh, I see. Okay. Let's see. Ask a question. Okay. This is like very informal because like Crowdcast is like not making any sense, but like let's pull this guy here. Come on. Where is it? Copy. Okay. What was your name? Ashley, I'll get to your question right after I get to this question. Okay. Speed skater moving across frictionless ice, so there's no friction, right? So there is no force counteracting it. Ice at 8 meters hits a 5.3 meter wide patch of rough ice. Okay, so there's now friction. She slows steadily, then continues at 6 meters per second. What is her acceleration on the rough ice? Okay, so we got a couple of things here. You guys know the kinematics equations? You guys have the equation sheet and stuff. Let me tell you, in my honest opinion as a student, like if you're gonna look at the kinematics equations on the equation sheet, I think that's like pretty useless, because if you're looking at the equation sheet, that means you don't actually understand what the equation means. If you understand what the equation means, then that means like you don't need to look at the equation. You understand what is happening. You could derive it on your own if you really wanted to. So this one I'll do a derivation. I did it last week, but because none of you guys are here last week, I'll just do it again. Okay, so there's a kinematics equation that is like, what was it? X. Okay, no. So delta x is equal to velocity initial times time plus 1/2 at squared, right? That's an equation on the equation sheet, I think. Let's look at the equation sheet. Let's make sure. I'm just being extra cautious. I'm like somewhat certain that is the kinematics equation. Images. Gosh darn it. Okay. Yeah. So x equals v initial t plus 1/2 at squared. So what is it? Actually, this is kind of somewhat related. So right now I'm going to derive these equations so you conceptually understand it. And then I'm going to solve the equation, solve the problem with like my derivation. Okay, so first off, like this is a kinematics equation where we try to find delta x. So we know 5.3. So let's just go back to the equation right now. 5.3, we know that velocity initial is 8, right? You know what? Let's just go backwards. Let's do 6. I'll explain why this also works. Okay, so 6 times time, right? We're trying to find time times 1/2 acceleration. We also need to find acceleration and we need to find time squared, right? Let me actually think about this a little bit longer. Let me also copy this down. Okay, I know I'm being really hypocritical, but it's kind of nice to have it right there in front of you. Okay. So we got 3 kinematics equations, and we are given. So this is like the noob way to do things, okay? Just to speed things up. So we got delta x is equal to 5.3. We need to solve for a. We don't necessarily need to solve for t, but it could be helpful, right? We have delta v or v initial and v final. So, okay, this one you shouldn't use, technically. This one you should use. Actually, this is like the one equation I don't know how to quite derive. But like this is v initial, which we have right here, 8 meters per second, and then v final, which is 6 meters per second, times acceleration, right? And we know x, which is 5.3. So this only has one unknown. When you have an equation, you have one unknown. That means you can solve it, right? Let's see. I try to solve it like this way I usually do it, but this way is also pretty simple. So you have v final, 6 squared equals v initial, 8 squared plus 2 acceleration, which you're trying to find x, and because you should make sure to keep track of units, meters squared. Meters squared, whole squared, and meters. Yeah? Okay. So what I usually like do these types of problems, I always like to make sure that the units match up. So this is like meters squared over meters squared, and this is equal to meters squared over second squared, and this is plus when you times meters over second squared, meters squared over second squared. So we clearly know that like everything here is like lining up correctly. But like I'm pretty sure you can solve this, right? It's just 6. It's just 36 is equal to 64 plus 2 times acceleration times 5.3. And like I do have a calculator right here. I can like even give you. This is your homework, right? If it's your homework, I'm not gonna like actually like solve it for you. I pretty much gave it to you right there. Yeah. Hold on. Let me see if I can actually derive this equation, because I've derived all of the other equations, but I've never actually derived this equation in particular. Let me see. 2 acceleration times distance. So this equation makes sense simply because the units cancel out, but I don't actually know how to derive these, so I was being a little bit hypocritical earlier. There's a lot of other ways you could solve this, so what you could also do is solve for t. So you can use this equation. Like, I'll be completely realistic with you. I was about to use this equation, solve for t, and then plug it back into this equation simply because I like conceptually understand how to like use these two equations, but honestly that's a lot slower than actually using this equation. Yeah. Okay. I'll think about like this equation and then I'll tell you how to derive it later. If I ever figure it out. I'll be honest with you, I don't actually know how to derive that quite yet. But I think right now, let's go to Ashley's question. Can you please explain tangent lines on a velocity graph? Okay. So, which one of you guys have taken calculus before? Like calculus 1, calculus AB? Yeah, no problem, Jake. But have you guys taken calculus 1 before? No? Okay. Taking it right now? Okay, Kaden, you're on good track. Ashley, calculus is the best thing that has ever been gifted to man. Yeah, physics is kind of tough because like the way that like we understand physics is simply through applied mathematics. And most of that mathematics is gonna be calculus. So yeah, let me just give you a quick crash course of calculus right now, okay? So just like really simple calculus, okay? Basically, the idea of calculus, at least I think Calc 1, is that when you have like the slope of a graph, right? So you have a slope here, like a tangent, right? The slope at a single point, you're going to get a bunch of other slopes, right? So and you take all the points and find all of the slopes and you graph it yourself, you'll find that the other graph is going to be like this. Okay. It's gonna look. So let's say that the tippy top is at 3x, right? You're gonna have like a graph that looks like this for the derivative, right? Saying that this is, so in terms of physics, this is gonna be x displacement and this is gonna be time, right? And it just purely in physics terms, right? So can you see why a little bit? Oh, no, I did that wrong. It's supposed to be like this. I've been using like general. Yeah, but can you kind of see why the graph would be like this? So at the beginning, you have a really high slope. It's going up really fast, and then it's starting to slow down, and then it becomes straight. The slope is 0, and then the slope, it starts going down, and that's when the slope is negative. So that is why the graph kind of looks like this, right? And when you use this as a mathematical term, right? It's like a really simple rule that you can use, right? So let's say that this is a graph of x squared. This is clearly not x squared, but let's just call it x squared, right? So if like dx dt, so that is a derivative of position, which is velocity, is equal to x squared. You take the derivative of that, d squared over dt squared, that's going to be 2x. And this is a quadratic equation, and this is a linear equation. You can see that in the direct relationship of the slopes of these lines. So that's like a really quick crash course of calculus. Yeah. So I like to think of it as slopes, because a tangent, you take that tangent line. Okay, tangent. I feel like tangent line sounds kind of dumb because it implies that there's an equation and there's like a y-intercept that's really irrelevant, but the y-intercept is completely irrelevant. Just think of it as a slope, right? So just like looking back at my thing, it's like if it's like really, really high, if it's really steep, like going uphill a lot, it's going to be a really high slope. If it's going downhill a lot, it's going to be a very negative slope. So that is like the basic overall idea, right? And there's what they usually do is give you an equation, right? So vt, right, velocity in terms of time is going to be 3x squared, and you have acceleration in terms of time. Like you do this power rule where you like take this and multiply it down here to be 6x, and you do this minus 4, which I don't think you really need to care about right now because that's like how you do the calculus. But yeah. So let me think. There was a practice problem I had about this. Do you guys want to do the practice problem, or does anyone else have like any other questions? Because I can like continue on this topic. I do have a practice problem for this. Anyone have any other questions before I continue? Yeah. Okay, if like no one has any other questions, like I'm just gonna go straight into the practice that kind of involves something about this loosely. So I'm gonna just continue. If you guys have anything, need anything to ask, just drop in the chat, okay? So this one is drawing the graph, right? So we need to like keep on thinking about these graphs and these tangent lines of velocities. A cop is chasing a burglar. For 5 seconds, a burglar doesn't notice a cop and he is at rest. Cop is running at him with constant velocity. When the burglar notices a cop, the burglar tries to confuse the cop by accelerating directly at him and then passing him. Resting at a constant maximum velocity, cop tries to turn around and chase him when this happens. In the end, the cop is running at the same speed he began with, but he is running in the opposite direction. Draw the displacement, velocity, acceleration graphs. So maybe I should have mentioned this earlier, but the slope of the displacement graph is velocity, and the slope of the velocity graph is acceleration. And like another way to say slope is rate of change. So the rate of change of displacement is going to be velocity. The rate of change of velocity is going to be acceleration. That's in another interpretation of it, right? So let's try to draw, what is it? Yeah, I'll show cop first. They got a cop, he's going at it. Let's do a nice graph, nice straight line. I can actually use straight lines. I realize that now. I have MS Paint is powerful. Okay, a cop is chasing a burglar for 5 seconds. Okay, let's do displacement first and time. So right now I'm like directly tracking the location of the cop. Like I'm not considering like what speed. Well, you do need to consider the speed. Like I'm just tracking the exact location. Oh my god! Like I keep on like doing dumb things on this stream today, but yeah, this is X. No. Yeah, I'm being a fool. So usually, yeah, this is I'm doing this right. Sorry guys, I'm like being a little bit dumb today, but. Telegraph, a cop is chasing a burglar for 5 seconds, so the first 5 seconds, the burglar doesn't notice a cop and he's at rest. The cop is running with him at constant velocity, so that means he is generally increasing at like a constant rate, right? Constant velocity means that it's a straight line up. When the burglar notices a cop, the burglar tries to confuse the cop by accelerating directly at him. So let's say he. Okay, let's do that here. For 5 seconds. So let's say that this tick mark is 5 seconds. And the burglar notices a cop. The burglar tries to confuse the cop by accelerating. directly at him and then passing him, resting at the constant velocity. The cop tries to turn around and chase him when this happens. So when he turns around and chases him, so that means he needs to change directions. So that means he has to, like, at some point de-accelerate. So that means he is going to slow down, right? So he's going to change direction. But it's going to be, like, kind of exponential, right? Because, like, when you change directions, you need to, like, apply a force. It's not like you're going to, like, flip from, like, 5 meters per second to -5 meters per second. You're going to, like, take some time to, like, change, right? So I guess you can kind of show that with, like, maybe, like, a slope top, right? Oh, God. I'm just going to use a brush for this. So there's going to be some acceleration, deceleration. So this one is going to put, I'm being a fool again. I wrote this question myself. It's going to look like this. Yeah. So this is going to be like an exponential, like, do you know, like, that x squared value? It's basically the second half. And then it's going to return to a straight line while he, like, accelerates. Velocity is that way, right? Now his velocity I think the velocity graph is a lot more interesting because, like, the x graph, like the displacement graph, is pretty intuitive, right? So this one, the velocity is constant, right? Yeah, this is a graph for the cop, right? Yeah. So you see that this is a straight line, right? And if you take the slopes of this line, right? Right, you're taking the slopes, but the slope doesn't change because it's just a line, right? When you think about, like, a line equation, like 2x plus 1 equals y, when you have, like, an x equals 3, the slope is still going to be 2. When you have x equals 5, the slope is still going to be 2. So it's pretty much constant, right? So the slope of this graph is the same. So that's why this is constant, right? And this one, decelerate, so you have to change the velocity. So the velocity, he turned around, right? So this is why he's going here, and then he's going straight down, right? So this is him turning around, and this is him going off at the same velocity he ended with. So let's say that this is like 5. I think I said he was going at 5 miles per hour. He's going pretty fast for that man. But 5 miles per hour, and about when he notices it, this is 5 seconds, right? So when you take the acceleration graph, right, acceleration time, you're gonna have, okay, so you take the slope of this guy, right? That first line at the beginning, that slope kind of looks like it's not increasing or decreasing. So you might think that he would be accelerating, but he's not. The only time he starts accelerating is when he hits here, right? And in fact, it's a negative acceleration. So what's happening here is that it's a straight line, and then, like, let me do this in color so you can actually see it. So he's not accelerating. You're taking the slopes of this line. Slopes are all 0, right? So the slopes are all 0 right now. You're taking the slope of this graph, which is negative, right? I didn't really think hard about, like, what negative value, but like you know that it's negative, so it jumps to whatever the slope is, and it clearly it's negative, so it's below the x-axis, which is t, and he continues at a constant velocity, and so it returns back to 0, if that makes any sense. Does that sound right? I need any more explanation, or everything good out there? Yes. Okay. You guys want to do the ones for the burglar? The reason why I chose this, I wrote this question, is because I remember reading a test like this. I'm gonna just do it anyway. Okay. So I'm gonna do this in blue, right? That's kind of weird. Cops were blue. Let's do black. Cops don't wear black and blue. Okay. So a cop is chasing the burglar for 5 seconds. The burglar doesn't notice the cop, and he is at rest. So this is the first 5 seconds where he's just chilling, right? Cop is running at him with constant velocity. And the burglar notices the cop. The burglar tries to confuse the cop by accelerating directly at him. So you kind of need to think about what's happening here, right? So you have, let's draw a picture, right? So you got your cop, right? Let's use blue because I have justified that policeman were blue, right? He was running and he is like, get out of my bank. And then you got the burglar guy, right? And he's like evil. So this guy is running this way, right? And we're assuming that this is positive displacement. But if this guy is accelerating straight at him, that means he has negative displacement, right? So that is why we have to draw this guy over here. This is going to be a curvy line because he's accelerating, right? So the magnitude of this is definitely wrong. Like the shape of this isn't right, but you kind of understand it's supposed to be this like, oh, I have no clue what that is doing. But you guys understand it's like this kind of x squared shape. It doesn't need to be that x squared shape, but if it's constant acceleration, that it's gonna be that x squared shape, right? And then the burglar tries to confuse him, so accelerate directly at him, then passing him and resting at a constant velocity. Okay. No. I'm being a fool again. Okay. Sorry, guys. I realized that if I'm using the same graph, I'm assuming that the burglar starts at 0, but if I want to have the graphs make sense together, let's say that it starts at, like, I should have justified this a little bit better earlier. You have this thing, and he is over here, and he's at 5. And of course, when t equals 0, x is equal to 5, or something like that, right? So he's actually starting over there. Hey, Jake. Just saw me kind of struggle with really basic logic. So you're not missing much. Okay. So let's just ignore the stupidity I was doing over here. Okay. So he is he's just chilling. So 5 seconds in, he's like, oh darn, there's a cop chasing me. And then he deaccelerates, right? He accelerates directly. Okay, let me think about this for a moment. So in this real life situation, he's gonna start running before the cop turns around. So he's gonna start going at it around here until he passes the cop, and then the cop starts turning around, and then he's gonna and then he's just gonna go off. He's gonna jet off to the distance, Yeah, I know, right? Like last time I was doing great. I had 0 problems, and this time I'm like struggling over like really basic logic. Okay, so you get the concept, right? So he's chilling, he accelerates, and then he maintains a constant velocity. That's basically what's happening here, right? So for the velocity graph, he starts at 0, right? Let's go back to the slope idea. Taking the slopes of these graphs, and all the slopes are 0. But then he starts, like the slope starts to tilt downwards, right? That means the slope starts to be down. I said that he started turning around before like the top season. It's like logically that makes sense in like a situation. And then he starts going at it, starts accelerating downwards, and he maintains like a higher velocity than the cop, which is pretty much that. Right? And then for this last graph, it looks strangely similar, right? You got an acceleration of 0. Technically, the acceleration is still in the negative direction. So you have this normal acceleration. Technically, it's larger because it's going faster than the cop. I didn't specify that in the problem I wrote. So, like, who really knows? Maybe he is, maybe he isn't. But, like, regardless, what counts is this graph, right? He is just accelerating, and, like, you take the slopes of these lines, it's still 0. So, basically, these are the graphs. And, like, you might notice they start to look very similar the later you go, right? And for those of you who understand calculus, right, when you take the derivative of something, right? So let's say you're taking like x of t is equal to 2x plus 3, right? That's 2x squared plus 3. So let's just make it a little bit more complex, right? Once you take the derivative of that, it becomes a velocity is equal to 6x. Is that squared? I think that's a squared plus 3. You can tell it already decreased in complexity, right? It's becoming more simple and more simple. And like, even though like these graphs initially look very different, when you look at the macro scale, like after a bunch of simplifications of that equation, they pretty much look the same, right? And that's just like the beauty of calculus. Okay, so that was that problem. I was like kind of, I don't understand the problem that I wrote myself, so that's why it took a little bit of time. But do you guys have any more problems you guys want to ask? So like just drop in the chat. I'm gonna just get to some kinematics problems. So yeah, that's the topic I'm supposed to be covering this week. So we're gonna start really simple. I am a bird flying 10 kilometers per hour. How long will it take for me to fly home? It's 23 kilometers away. How far do I fly every 10 seconds, right? So 10, oh, you wrote a question? Is it in the questions thing that I can't see? Yeah? Oh, I see. Okay. Oh, it's okay. Do you guys want to do like the kinematics questions I wrote during class, or yeah, let's just take a look at what's happening here. 2 cars are traveling along a straight line in the same direction. So I feel like this is like written by a legitimate teacher, not me during like a comp sci class that I was supposed to be paying attention in. But let's see, 2 cars are traveling along a straight line in the same direction, so they're going. Let's assume that their velocities are both positive. The lead car at 25 meters, the other car at 30 meters per second. At the moment, the cars are 40 meters apart. The lead driver applies brakes, causing her to have an acceleration of negative 2 meters per second. So when you have a negative acceleration, it doesn't necessarily mean they change direction, even though they eventually will. It just means they're slowing down. And eventually, if you continue to have that acceleration, it'll go backwards. How long does it take for the lead car to stop? Okay. Let's go back to like this like crazy ass. Okay. 2 cars traveling 30 meters, 40 meters. So first, let's do this first problem. 30 meters per second. And this person's deaccelerating at 2 meters per second squared. That's a pretty simple question to ask. 2 meters per second squared. So basically, I guess, you know how like distance is equal to velocity times time, right? Because this is meters is equal to meters over seconds times seconds, right? And this all crosses out. And it's just meters equals meters. So this is kind of the same thing, right? So you have velocity is equal to acceleration times time. And I think that's one of your kinematics equations. It's pretty simple, really easy to derive, right? So you want a delta V, right? And you want to end with negative 30 because if you lose 30 meters per second, that means you're back to zero because 30 minus 30 is zero, obviously. Is equal to acceleration, which is 2, negative 2 meters per second times time, right? And time is just going to be 15 seconds, right? And just going back to the units thing, this is like really, really important, right? You always want to make sure that your units cancel out. So it's going to be meters per second equals meters per second. So everything is perfect. Let's see. Assuming that the chasing brakes at the same time. Assuming that the chasing brakes, I'm assuming that chasing car brakes at the same time as the lead car, what must be the chasing car's minimum acceleration as to not hit the car? How long does it take for the chasing car to stop? Assuming that the chasing car's brakes. Yeah. Okay. What must be the chasing car's minimum acceleration? Okay, so basically, oh no, where am I going? I'm going too high. So you have 30 meters per second, 25 meters per second, 40 meters apart. Okay, so basically they stop at the same time. This is one of those like funky graph questions. I mean, let me actually like use snipping tool again and just like copy paste. Okay. Okay, 2 cars are traveling on a straight line in the same direction. Okay. So the moment cars are 40 meters apart. Okay, so what I'm gonna solve first is that like how long it takes for them to get apart, just to see where they are, right? So it takes them 8 seconds to be apart because so distance is equal to velocity times time. And it's going to be like 30 times time minus 25 times time, which is 5t is equal to 40 meters, right? So t is going to be 8 seconds. That was like a really quick maths kind of thing. But I believe driver applies brakes, causing her to have. So they're 8 seconds in. So this person 40 meters away. So 200 meters. This guy is at 40 meters. Acceleration at 2 meters per second. 25 meters per second. 30 meters per second. Okay? Let's see the rest. Let's look at the problem again. Chasing car. What must be the chasing car's minimum acceleration as to not hit the car? Oh, I see. Okay. This is a little bit contrived. But, okay, so what I think, it feels like a semi-difficult problem, but it's not unsolvable. So, we're trying to find you just need to make sure that these two cars do not hit, right? So you have this equation that's like 1/2 at squared is equal to like 40 meters per second. Let's see, acceleration. I'm actually not quite sure what to do with this problem. Let me see. Let me think about this a little bit harder. Okay. Let's solve for how long it takes to get here, right? So 1/2 at squared is equal to 40. So by the time it gets there, it's going to be 80 is equal to 2 times t squared, which is 40 times t squared. So it's going to be 2 root 10 seconds to get here. Sorry, I'm just like a little bit, I'm not sure what to do with this one. So then that means the velocity is going to be 4 root 10, right? Well, you know what? Let's just, I think I'm like getting like stuck on problems that I shouldn't be. How long does it take for the chasing car to stop? So that implies that, oh, okay. So when this car applies brakes, this car is having a forward velocity, right? So what we're trying to do here, okay, I finally understood the question. Okay. Sorry to like keep you guys out there for so long. But basically, we just do not want these two cars to hit. So when this car applies brakes, it's still going forward. When this car applies brakes, it's still going forward, but then it's going to go backwards, right? And that's ultimately what's going to happen to both of them, right? So distance is equal to v delta x. So this is the original equation I was going with, plus 1/2 at squared, right? So, okay, so we know delta x, right? We have 200 meters, 240 meters, right? And then so we have, so car one, the chasing one, was going at, what was it, 25 meters per second. Meters per second. No. Oh, did I write this equation wrong as well? Meters per second squared. Hold on. This is time. Velocity times time. Velocity initial times time, right? So we solved that. This is going to take, I just wrote down the solution for time earlier and then I just deleted everything. Gosh darn it. Delete car at 25 meters per second. Another car at 30 meters per second. 40 meters. Oh. So it was 8 seconds. Yeah, 8 seconds. So there were 8 seconds plus 1/2. We don't know the acceleration yet, but we're going to have t squared. And that's going to be, okay, so 8 plus t. And this is going to be 8 plus t because that's total time. I'm confusing myself again. But, oh my god. So look at the equation. Yeah, but that's correct. That's correct. Okay. And then this is 8 plus t. So we want to find like the total amount of time. That's why you have to do 8 plus the time. And then you have the other car car that is in the lead that you don't want to crash into it. You have that at 30, also at 8 plus t plus 1/2. You know that this is -2, and then 8 plus t squared, right? So what you're going to do is set these two equal to each other, right? Because if they're equal to each other, that means they hit. And that means that that is the minimum velocity. You just need to have that velocity but lower, right? So you take this giant equation, solve it, combine all the like terms, and then yeah. But you need to solve for t. That's a problem too. I just realized that. I think that no, you can divide it out. You can divide it out. Yeah, so you can get rid of an 8 plus t term, 8 plus t term, 8 plus t term, 8 plus t term. And so the final equation that we can have is 25 times nothing, 25 plus 1/2 8 plus t times acceleration is equal to 30 plus 1/2 times -2 times 8 plus t. Then we need to find t, and that's also the second part of the question that they're going to ask us. So they're probably going to ask us to use a different kinematics equation. Okay, we're about to get there. So I think we're almost there. Velocity initial, velocity final. I don't know which kinematics equation to use. V final over initial to acceleration times distance. Do you guys have any input out there? You guys have any recommendations on what to do, or? And sorry about that. I'm a little bit confused with this question as well. I can see why this is a little bit difficult. Okay. But yeah, sorry about that, Ashley. I can't quite figure it out. But I'm gonna be thinking about this tonight, and so I'm gonna get really frustrated over this. X equals 1/2 inertia plus v. So I guess, yeah. Sorry about that. No, it's okay. I think that their notes. I mean, this is just kinematics equations. It's just manipulating the kinematics equations to what you want. And right now, what we're trying to look for is t. I don't know if v initial or v final. Yeah, sorry about that. Couldn't quite figure it out. I'll keep on streaming until I figure this one out. I'm not gonna stop until I figure this out. Because I know if I stop right now and I still haven't solved it, it's gonna be bugging me forever. So I know that that's an equation that I can use. A plus 2 times L. Put it here. Initial plus acceleration times time. But we don't have v final. V? No, it's just it's like straight acceleration, so you can't even find V final. That's just like really simple. And x is equal to V initial plus V final. So it's this is basically equal to 1/2 AT squared, which is part of a derivation of that. No, that's not. That's just like kind of, yeah, it's just acceleration times time. So 25. So TA is going to be V final. Plus 4A plus TA over 2 equals 30 minus A minus T. Yeah. Huh. There's no V initial, there's no V final. Okay. So let's say V initial and then V final is going to be 40. Like just say that like they see how long it takes for them to get to a complete stop, right? So you have T is equal to. So we know that it takes T to be equal to, what was it? 2 meters per second. So it's going to take 15 seconds for the first fast car to stop. And it's going to be 15 seconds. V final, V initial, 30, 15. Huh. So V initial plus V final is going to be 30 times T, 30 times 15. Oh, I can't even do that in my head right now. Calculator also doesn't work. 450? 15 times. Oh, it's 225 meters. So we're trying to find that. Huh. So I guess you just need to have it less than 40 meters, right? You just need the acceleration. So by the time that T stops, so within 15 seconds. Yeah, that's such a. Okay, I got this. Okay. I think this kind of makes sense. So this car comes to a complete stop after 15 seconds, right? So we just need to find the other car that stops before it stops. And then accelerates all the way back. 265 minus A times T. So first off, it has to. See if you guys have any recommendations right now. I should keep up to date with. Nah, it's okay. Like I'm just like kind of brain farting right now. I feel like I definitely jinxed it at the beginning of this stream. I was like, I got this handled. I do a lot more things that are far more difficult, and then I'm like here at like a physics 1 problem, and I'm struggling. Okay. That is not safe for it. This is fast. So it definitely needs to be accelerating a lot faster, or else it's gonna hit. Nice constant. This is gonna keep me up all night. Oh my god. 18 seconds? So it's gonna be 1/2 8. You know, I'll be honest with you. I know it's gonna keep me up all night. I'm probably gonna ask some of my other physics friends to like look at this as well. To like just see what's happening here. This is like so simple. I don't know why I can't like figure it out. I'm not saying it's simple, I'm just saying that like this looks like a really simple problem, but I'm like technically my time is up, but like technically right now I feel really bad because I can't solve this problem. You don't have to. I feel pretty bad about this one, but I do have many more kinematics equations. I'll do like another one that like I wrote earlier. Pressing the brakes of my heart. Okay, you know what? I'll teach you the trick that I learned in college concerning acceleration and drop questions, right? So I remember. So honestly, I'll tell you one thing. My favorite equation is just 1/2 at squared value, right? This is like the derivation of like basically half of the other equations, right? So basically it's saying that when you have acceleration, I guess like the best way, so when you take an integral, right? You take the area under the curve, okay? So you have like acceleration times time squared. So you have velocity times time. And if you find like, this is velocity initial times velocity final. This is like just a really easy way to explain the derivation of this, right? So this is like delta V and this is delta T, right? And when you find the area under a curve, it becomes the integral. So the integral velocity becomes displacement. So once you find like the integral under this area, it's going to be like displacement, right? So this is base times height. So V times T times 1/2. But this, because this is displacement, I also want like a T squared value. So 1/2, I'm also screwing this up. Hold on, I'm screwing everything up today. Anyway, now it's 1/2 at squared value because Vt, when you take the integral of it, it becomes 1/2 at squared, basically. But that's because it's a lot of fancy calculus. Basically, what I'm trying to say is that you want to use this 1/2 at squared for a lot of things. And this also comes with the initial V plus T value is equal to delta X. This is how you like solve a lot of kinematics problems. So I dropped a ball at 10 meters. So you have a ball and it's 10 meters high, right? And will it hit the ground, right? What velocity will it hit the ground? So I have two problems. Like when will it hit the ground? And secondly, at what velocity will it hit the ground? So you're trying to solve two problems, but if you solve for one, you solve for the other, basically. So if we know that it's like acceleration on Earth is 9.81 meters per second squared, you can just solve for this 1/2 at squared value. And since velocity initial, if you drop it is 0, you can just get rid of this value. So you have an acceleration is 9.81, and you have T delta X is equal to 10 meters. You can just solve 9.81 times 1/2 times t squared is equal to 10. 20 is equal to 9.81 t squared. Okay, let's just round gravity to 10. And let's just say t is going to be about square root of 2, right? Because I'm just like very grossly rounding the acceleration due to gravity, right? So if t is about square root of 2, then you drop the ball, right? So you've already found like the first thing. When will it hit the ground? About square root of 2 seconds. At what velocity will it hit the ground? So if we know that acceleration is 9.81 meters per second, we grossly round it to 10 meters per second squared. We can just do the same thing where we're doing with like the velocity, distance is equal to velocity times time. That means velocity is equal to acceleration times time, right? So acceleration times time, it goes for square root of 2 seconds times 10 meters per second squared. It's just like velocity is just going to be square root of 2 times 10 meters per second squared. I actually have a calculator, it just doesn't work. But that's like kind of how I do all drop questions. I basically ignore everything and just solve for 1/2 at squared, simply because it's such a beautiful equation. But yeah, sorry about that, guys. I know the stream was like pretty, like, I wasn't on top of like all my calculations today, and I'm like kind of struggling a bit. But yeah, I'm usually not like this, I think. But yeah. Anyway, I do this every single Thursday. I don't want to say that, that's ugly. Okay, post video. Okay, anyway, sorry about that. I know this stream was kind of slow, and like a lot of it was just me struggling over a problem. Sorry about that. But I do problem solving practice every single Thursday. So if you guys want to come back next Thursday, then like feel free to come back. If you guys need to like study for a test, drop like just info in the chat of like what kind of test you have next week. So yeah. Anyway, I'm gonna like head out like right about now. If you guys have like any last things to say, let me just make sure I have it. Okay. Anyway, I'm gonna head out now. Sorry about like not being able to solve your problem. You should go ask your teacher. Oh, thank you for coming. I appreciate y'all coming to like just like see the struggle. But I'll be here next week. And hopefully I'll be more competent. Okay. Bye.